Good morning, everybody. So let's come back into a couple nomenclature examples, and then we'll head into chapter 3 today. So last time we were talking about, at the very end of class, methane, ethane, propane, butane, these being saturated hydrocarbons. So methane was where we had saturated carbon with 4 hydrogens. So carbon can form 4 bonds, so this would be methane, of course. Ethane is where we have 2 carbons bonded together. And of course, the bonds to carbon count as a bond to carbon, so we only get CH3s on either side. So we have C2H6 is our formula for ethane. Propane is having 3 carbons, so to saturate them, we end up with 8 hydrogens in total, so 3 on the ends on each of those carbons, and then 2 on the carbon in the middle. Butane is the 4 carbons. If you count the number of hydrogens, it ends up being 10. If you're like, well, how do you get 10, or how do you know 10 for butane? You'd be taking, your 4 carbons, and then just thinking, well, how many hydrogens do I get on to the carbons? 3 on the end positions, so CH3 on the ends, and then 2 CH2s in the middle. We can condense this into CH3, CH2, 2 CH3, just to make sure you're seeing the 6 for the end CH3s plus the 4 hydrogens in the middle to come up with 10 total for butane. And then from 5 and up, I think it's a little bit easier, at least up to 10, because we just go penta, hexa, hepta, octa, nona, deca, the sides of a hexagon. We'll do a couple examples of the bigger ones on a slide or two from now. But if we replace any one of these positions with the hydroxyl group, that OH group, then we have the organic alcohol. So methanol is just where we take a hydrogen in methane and replace it with that OH group. And then if we do the same thing on ethane, we get ethanol. We could replace any of these hydrogens in methane and methanol and get the exact same compound. So if you're looking at methane or ethanol and saying, well, why didn't we choose a different position to put the hydroxyl group? We could have. We could have left this one as the H and then put the hydroxyl group in that position, and this would have been the exact same molecule of ethanol. Now when we get to propane, we actually have a choice if we put it on the middle carbon or if we put it on one of the CH3s. So the 1-propanol is where we put that OH group on either the end carbon or the first carbon. So if we choose either of those 2 carbons with the CH3 groups, replace any one of those CH3s with that OH group, then we would have what we call 1-propanol. And then we contrast on the next slide with 2-propanol. So 2-propanol will be where we put the hydroxyl group on that middle carbon. Now, we're not going to really make you responsible for knowing how to number things like 1 verse 2 butanol, 1 verse 2 verse 3 pentanol, things like that. We're not going to get into the numbering system in terms of testing you on the proper number. But I think one thing that's worth noting is that these 2 molecules here are isomers of each other. So isomers are different compounds that have the same formula, and they have different properties. And so I think it's just worth pointing out that 1-propanol is different than 2-propanol in terms of its melting point, boiling point, density. So its physical properties are a little bit different. Maybe similar, probably pretty close, but not exactly the same. So isomers tend to differ in some way, even though they have the same formula. And so one thing also worth pointing out is if we were to kind of flip this molecule or just put the hydroxyl group over here, we have the exact same 1-propanol molecule. So you have sort of 6 choices for where you put the hydroxyl for 1-propanol. We could have put the hydroxyl group here, or here, or here, or here, or here. And that would be the exact same molecule of 1-propanol. Sometimes we get a little confused on the numbering system or just thinking about molecules. We have to almost think about 3-dimensional shapes, which we haven't talked about how to sketch and determine 3-dimensional shapes. We don't get there until chapter 9. But once we get there, we're going to see that there's like 6 different ways we could sketch 1-propanol. There's 2 different ways we could sketch the 2-propanol, and those would be the exact same molecules as each other. So we have like 2 different 2-propanols that are the same as each other, 6 different ways we could sketch the 1-propanol. So when we start thinking, or if you see examples in the book on numbering hydrocarbons, like the alcohol positions, don't worry so much about that. You can understand the complexity. You can understand that it's trying to name isomers a different way for compounds that are isomeric. Okay, so I just wanted to point this out. There's a few other examples in the nomenclature at the end of chapter 2 that we're not getting into. So I think they get into some different sort of isomers of the hydrocarbons themselves, so how you could rearrange the carbons. Like when we look at, let me move to this next example to kind of show this. When we look at pentane, we're just kind of picturing putting the 5 carbon atoms in linear sequence. The book goes into how you would name and how you can think about different isomers and things like pentane, on how we could maybe put one of the carbons here instead of over here, and then this would be an isomer of pentane. We're not going to get into that business and name those different compounds. So just know that that's materials in the very last part of the last section of chapter 2, and you're not going to be responsible for that content. And there's no homework problems. There's not a lot of daily, I don't think there's any daily quiz problems on those topics that you'll run into. So I just want to make you aware, if you look at the end of chapter 2, you might see some of those topics. So for pentane, if we're trying to come up with the formula, so remember nomenclature, the business here is from the name, can you give the formula? If I give you the formula, can you give me the name? Let's not worry about predicting why these compounds exist. That's not what we're talking about in chapter 2. We're not trying to say, well, why did we name this and not that? Why does this exist and not that? That's not the purpose of chapter 2. It's just if we show you the name, sketch the symbol. If we give you the symbol, get the name. So for pentane, we're just, penta for 5 carbons, and then just 4 bonds each. So pretty easy if we're just sketching it out here. If you want to take the time, that's fine to sketch this out. So that's one way we can come up with the count of hydrogens. We could also, again, use that other approach, CH3s on the end, CH2s in the middle. We're going to have 3 CH2s, the NCH3, to give us 5 total carbons. So that's going to be 6 plus 6, so that'll be 12. So this should be C5H12. And so again, you could count here as well and come up with that count of 12. If we had a formula C7H15OH, so I think we know this is some kind of alcohol, but it's an alcohol of the hepta. So hexa is 6, penta is 5, of course. The only, so octa is 8, nona is 9, deca is 10. So decane would be the C10 hydrocarbon, nonane would be the C9 hydrocarbon, octane would be the C8 hydrocarbon. So the C7 hydrocarbon is heptane, so this would be heptanol. And again, if you're thinking, well, how did we know for sure, or how many hydrogens would heptane have? So heptane, again, we just have the CH3, CH2s, and the NCH3, and then we're going to have 5 to get 7 total carbons, so 5 CH2s. And so 6 plus 10 is 16. So heptane would be C7H16. Just making sure we see how we get heptane, and then replacing one of the hydrogens with the hydroxyl group gives us heptanol. And a little quick review on like P4010. So when we're thinking about nomenclature, try to think about like the thought I go through on naming a compound. Is it ionic or is it molecular? If it's ionic, it contains ions like metal ions, maybe ammonium ions, and other counter ions like anions. If I see only non-metallic elements, I'm probably thinking it's a molecular compound. So P4010, non-metallic element. So this is a molecular compound. That helps me then try to think, is it an acid, is it a hydrocarbon, is it an alcohol, or is it maybe a binary compound? So this would be one of those binaries. A binary is the one, if you remember, it contains 2 total elements, and then any proportion. And so then we just use the prefixes out in front. So we use tetra, phosphorus, and then deca for the oxygen. So deca oxide. And the only little tidbit is that last element goes with its IDE ending. So we go oxide for the ending for oxygen. So the first element just keeps its ordinary name. So the next one down, again, I'm thinking ionic versus molecular. When we get to the acid, sometimes it gets a little bit, like we get a little bit confused maybe sometimes when we pictured carbonate, CO3 2 minus, and we were adding like H plus to it to neutralize the charge. We might then think this is an ionic compound because we're kind of bringing what look like ions together. But once the hydrogen's attached to carbonate, they form those molecular covalent bonds with the hydrogen atoms in carbonate. So we end up forming a molecular compound here. So our acids, all the acids we've named are molecular compounds. So when we look at something like HCl, it's molecular, not ionic. It can ionize, we talked about in chapter 4, so later we talk about really why we call things acids is when they hit water, they can dissociate. So we'll talk about those processes in chapter 4. But for here, just picture your acids as molecular compounds. It's an acid, so we name it as being an acid. And it's an acid of carbonate. So we look at the CO3 2 minus ion was carbonate. And so we go ic acid off of carbonate. So carbonic acid. So the 8s go to ic acid. PO3 3 minus in this acid form. So this is also a molecular compound, also an acid. We usually see the H's out in front. We usually then see the anion that they're attached to that we learned how to name. So this would be phosphite. So this is the acid of phosphite. And ites go to us acid. So this would be phosphorus, OUS acid. The next compound down, we see potassium. We see an anion here. This is an ionic compound. So an ionic compound, the atoms keep those charges like in the compound. So it remains as being an ionic compound. So we have then potassium for potassium plus. And then the HSO3 minus ion is the hydrogen oxy anion of sulfite. So that would be potassium hydrogen sulfite. Now the next one down, calcium's a 2 plus, H2PO4. PO4 was a 3 minus. Each of the H pluses brought a 2 plus charge to that molecule. They don't keep the charges though once they bond together is the idea. So once H2PO4 forms, the charges distribute across the molecule. So then the overall ion picks up a negative charge, a -1 charge. So once those charges mix together, we get the minus charge for the H2PO4 ion. It took 2 of them to balance out the charge with calcium. So this would be calcium and then dihydrogen phosphate. So dihydrogen phosphate is the name of the H2PO4 minus ion, if you recall. Now, in the notes, there were some extra slides on nomenclature. I made a video of those and put them up after Wednesday's class. So there were a couple slides on naming in the notes. If you're wondering about those, I put a video up of those. I figured today let's do a separate set here just to kind of keep pushing forward in terms of naming compounds and making sure that we can look at a compound, categorize it, think ionic, is it molecular? If it's molecular, is it an acid, hydrocarbon, alcohol, or a binary? Like if you can categorize the compound first, will help you generally find the right category it should be named into. And then most of the nomenclature stuff on exams is multiple choice. So you're usually not typing in like an actual answer, so that's good because sometimes the spelling gets a little bit nuanced, but just get good at looking for the choices given like 4 or 5 choices. Daily quizzes have a bunch of nomenclature questions if you're looking for some practice. So that takes us kind of through chapters 1 to 2. So we've kind of gone through, elements, atoms, molecules, compounds, mixtures. We talked about energy, kinetic energy, potential energy, energy conversion, the joule from chapter 1. We did some sig fig problems, dimensional analysis, conversions. Got into the experiments that led to the discovery of modern atomic theory, the protons, neutrons, electrons. So we had the cathode ray tube experiment help discover the electron, the subatomic particle. And then the oil drop experiment helped us understand the actual mass of the electron and how light it was. Also helped us establish the charge of the electron. Later experiments determined the nature of the proton and the neutron. And then the nuclear model was then supported by taking the alpha particle and shooting it at a thin sheet of gold and seeing that some of the particles were backscattered, and they were backscattered due to hitting the massive nuclei. So that kind of got rid of the plum pudding model, if you will. Do you remember the one model where we just had all the subatomic particles, electrons, protons, neutrons distributed in an atom? Well, this model from Rutherford's gold foil experiment led to that nuclear model where we think of the nucleus containing the main mass of the atom, the protons and neutrons. That got us into AMU scale atomic weights. We'll further get into like the mole and kind of using the periodic table to work out masses and moles and those units later in the chapter 3. Getting into molecular and ionic compounds and naming compounds towards the end of chapter 2. So what's up in chapter 3? So chapter 3 gets into chemical reactions. So, and then quantifying details of chemical reactions. The first half of chapter 3 is a little bit more in terms of understanding the mole unit, understanding how we can come up with formulas and experimentally how we determine formulas from experiments, and then quantifying aspects of chemical reactions are like the last two sections of the chapter. Okay. So on the first day of class, we blew up that hydrogen balloon. If you remember, the reaction that was going on was 2H2 gaseous molecules plus O2 gas were reacting to form the compound water. Now, sometimes you might wonder, how do we know what physical state these substances are in during the reaction? Sometimes it's obvious, sometimes it's not obvious. Sometimes you know, sometimes you don't know. In the nature of that reaction where we were putting this in a balloon, heating up the balloon, I think we can be fairly confident that we were starting with gaseous H2 and O2 because they're gases at room temperature. So they were in a balloon that was filled up. So I think we knew they were gases. And as soon as the balloon popped, we didn't see like a puddle of water form. So I think you can imagine the flame took the water vapor into the air as a gas. So usually in a reaction, we're going to be indicating a few things. We're going to be usually indicating the physical states of our reactants and products. We're going to be indicating the actual formulas of those molecules of the reactants and products, like H2 is molecular hydrogen. So hydrogen exists as two hydrogen atoms bonded together, and we have a collection of those in an H2 sample. O2, two oxygens bonded together, water, two hydrogens for every one O. So we're indicating the molecular formulas of our molecules and our formulas. And we also have to use our coefficients. So our coefficients are the numbers like the 2, the 1, the 2. So these are our coefficients. So these are the proper reacting units to balance out the hydrogen and oxygen atoms on both sides of our reaction. So here we have 4 H2s, 4 H2s, 2 oxygens, 2 oxygens. So the coefficients are how we balance out the reactant and product so that we're not creating or destroying mass during the course of a reaction. We're just simply changing the nature of what's bonded to what during the course of a chemical reaction. Sometimes you see symbols like this in a reaction. The delta symbol is just to imply heat or a spark. So the delta symbol is usually meant to imply that you give a spark to the reaction, and there's like a chain reaction that then occurs with that spark, leading from the formation of the reactants into the products. So sometimes a spark, sometimes this means heat. Sometimes it means heat up a reaction, is sometimes why you see a delta symbol above the reaction arrow. And I think this goes without saying that the left side is before, what's present before, and the right side is what's present after. So this is the before. This is what we have formed after. And then later what we're going to see towards the end of the chapter is that you can imagine mixing up random concoctions of elements or of reactants, and then sometimes one of those reactants could remain after the reaction completes. So when a reaction takes place, all of the reactants in the reaction will have completed to form the products, but if we mix together, like let's say we had 10 parts of hydrogen to 1 part of oxygen present in the balloon, we would have had some hydrogen left over. So we would have had some leftover hydrogen after that reaction took place that would not have reacted. So we could have an excess reactant that also remains after we have a reaction taking place. Now, early in chapter 3, we established a couple general types of reactions that are worth understanding. The nature of those reactions. One of those are combination reactions where we're taking like two things, combining them to a third, like an A plus B goes to C. This is sometimes useful because a lot of compounds form from elements combining in a combination reaction. So if you combine sodium and chlorine in their elemental forms, elemental form of sodium solid, remember all of our metals are solids except for mercury. So we have sodium metal. And then most of our nonmetals are gases, with the exceptions of things like carbon, which is a solid, bromine, which is a liquid, iodine's a solid. So if you look at the periodic table, the black shaded elements, solids at room temperature, the blues, too, bromine and mercury are liquids, and the red are gases at room temperature. So Cl2 is a gas at room temperature. They're reacting to form sodium chloride. And again, I'm not sure every example of reaction is going to be so easy to predict the physical state, but sodium chloride has a really high melting point due to the fact it's ionic. The plus-minus attraction really makes for a strong attraction of all these ions. So NaCl is Na plus Cl minus, Na plus Cl minus. It's an extended structure in like 3 dimensions of plus and minus ions all interacting with each other. But now you take sodium and chlorine reacting together, you form the common ions of sodium and chlorine, so plus and minus. And then to get the proper balancing here, we're going to put 2 in front of sodium chloride to balance out the chlorines. So we have 2 chlorines on both sides, and then 2 in front of sodium. And so another thing that should happen during the course of reaction is the charge should be balanced. You know, we started with 2 elements that were uncharged, and we ended up with a product that's uncharged. And that's important because if we had somehow made an ion on the product side without having started with a net ion on the reactant side, we would be like making electrons. So we're not creating or destroying subatomic particles during the course of a reaction. We're just making sure we start uncharged and uncharged. So our charge should be balanced, and it is. Aluminum and oxygen, I actually wrote this reaction. I was kind of like debating even writing it on like the first day or second day of class when we were talking about some basic chemical reactions. But aluminum and oxygen react to form the common ion of aluminum, which is aluminum 3+. Now we know the common ion of oxygen is O2-. And so they would react to form Al2O3. So just the common ions of aluminum and oxygen to form Al2O3. And if we want to balance this out, we have 3 O's here, 2 here. So what if we do a 3 in front of O2 to go to 6, and then a 2 in front of the Al2O3 to also give us 6 oxygens. And then that gives us 4 aluminums, so I need 4 Als. So 4 aluminum plus 3 O2 go to 2 Al2O3. Now again, Al2O3, by balancing out our charge, we have a charge neutral molecule, and we started with neutral aluminum, neutral oxygen. If you don't see a charge indicated, of course the substance would be neutral in charge. So that's our combination reaction, and our basic reaction that we'll know is just elements can combine to form an ionic compound if we're taking metal and nonmetal elements and combining them. Sort of the opposite reaction to a combination is a decomposition reaction. Now you could take like sodium chloride and return to the elements. You could do that through what's called electrolysis. So by adding electricity to be your energy source, you could take what really should be an energy uphill step. Like it's really hard to take sodium chloride back to the elements because in terms of an energy landscape, sodium chloride's down here. It's at the bottom of the hill. The elements are at the top of the hill. But you can use electricity to give you the energy to push them back to their elemental form. So through electrolysis, you can take things like sodium chloride back to its elements. You could take H2O, water, back to hydrogen and oxygen. So one of the ways you could get hydrogen as a fuel source, if you wanted to come up with like a hydrogen fuel cell, is maybe you're doing the electrolysis of water to get your hydrogen, and then hydrogen eventually reacts with oxygen in your fuel cell to return to water. So you're not really creating energy, but you're just creating a fuel source or creating an energy storage source through creating hydrogen. Okay, so a decomposition reaction, the opposite of combination. One of the examples they have are carbonates reacting to form oxides in CO2. These being reactions that take place through the addition of heat. So not a spontaneous reaction, but one, if you heat up this mixture, you can get calcium carbonate to form calcium oxide plus CO2. This is actually a main feedstock of like limestone being a main feedstock of calcium oxide used in like cement industry. So this reaction here is pretty important. So the formation of cement is actually giving off CO2 gas. So if you want to make CO2, or if you want to make cement, you're producing carbon dioxide in the atmosphere. So sometimes we don't think of just building projects and some of the materials themselves leading to CO2 in the atmosphere. Sometimes we only think it's automobiles and airplanes, but it's also the cement industry and other industries as well. So we see CO2 as a byproduct here. So we're going from calcium 2 plus, carbonate 2 minus in their ion forms to calcium 2 plus, O2 minus, and then CO2. Just kind of pointing out that the charge of calcium remains 2 plus, and then the charge of oxide is the same charge of carbonate. Now when we go to predict the products from a similar type of reaction, if we took the carbonate of iron, where iron here is in the 3 plus state, how do I know iron's in the 3 plus state? Well, just from looking at the charges here. So carbonate's a 2 minus, so I have a 6 minus coming from the 3 carbonates. So 2 minus times 3 is 6 minus. So from the 2 irons, I have a 6 plus. There's 2 of them, so they each have a 3 plus charge. So this would be iron 3 carbonate in terms of nomenclature. So iron 3 carbonate, when it's heated, ends up forming iron still with the 3 plus charge, oxide ion with the 2 minus charge. So I end up forming Fe2O3 as the one product, and then the other product being CO2. And then I had 3 CO3s, so I end up forming 3 CO2s. So I get Fe2CO3 forming Fe2O3 plus 3 CO2s. So I've just taken 3 carbon dioxides off of carbonate, leaving behind the 3 oxide ions. And then this would be balanced as written. So that's just a basic decomposition reaction, or metal carbonates decomposing to metal oxides plus CO2. And then probably the most important reaction, the one that we probably use the most in our lives, the one that we'll talk about a lot in examples, are combustion reactions. So combustion reactions are where we take hydrocarbons plus oxygen and then give them a spark. So give them a spark of electricity or a flame, and then we can form CO2 and water as the byproducts of that hydrocarbon combustion. So we're forming CO2 and water as our main products. So if we want to balance, I didn't leave a lot of room here, but CH4 plus O2 goes to CO2 plus water, sorry. So CH4 plus O2 goes to CO2 plus water. If we want to balance maybe the hydrogens first, I put 2 in front of water for 4 hydrogens on both sides. So that gives me 2 and then 4 total oxygen atoms. So I need a 2O2 to put this into balance. So CH4 plus 2O2 goes to CO2 plus 2 waters. And so then I have ethanol reacting with oxygen. Then we're also going to form CO2 plus water. And then if we look at the hydrogen count here, we have 6. So we're going to form 3 waters. I have 1 oxygen already in ethanol, and so that's already 1. So I have 3 here. Oh, I need a 2 in front of CO2 to balance out the carbons. So I need 2 CO2s to get 2 carbons on both sides. So that gives me 7 oxygens on the product side. So 4 plus 3 for 7. And then I need a 3 in front of oxygen. So the 3 times 2 is 6, plus the 1 in ethanol give me 7. So we have to just make sure that we count the oxygen in ethanol as being one of the O atoms in the reaction. So we have 7 O's when we go ethanol, ethanol plus 3 O2 goes to 2 CO2 plus 3 water. So the key here is we can predict the products, and then we can balance the reaction accordingly. So then let's talk a little bit about formula weights versus molecular weights. So for like any molecule, the formula weight, we're going to get the formula weight for like CH2 or for C2H2, and also its molecular weight by simply just adding up the mass of the atoms in the molecule or the mass of the atoms in the formula. So for C2H2, it's a molecular compound, right? It contains non-metallic elements. So when I'm looking at a molecular compound, I can give a molecular weight for the molecular compound. So for CH2, the formula weight is going to equal the molecular weight. They're going to be exactly the same thing because the formula is the molecule. Like C2H2 is the formula of C2H2, and it's a molecule, it's a molecular compound, so it has a molecular weight. And so then when we go to determine the molecular weight, we go to the periodic table. So we go to the periodic table and just look at carbon. So carbon on this one here is 12.011 atomic mass units. We need 2, so we do 2 times that for the 2 carbons, and then plus 1 times the mass for hydrogen. Now, often a question that you'll have is how many of these sig figs do you use on an atomic weight? Like for hydrogen here, it says 1.00794. I try to get in the habit of using, usually in most like textbook problems, when I'm doing a text problem, when I'm doing like a homework problem, when I'm doing a test problem, I get in the habit of using 3 sig figs for like the lighter elements. So when I have only like 1 sig fig to start a mass, like 1.xxx, for like hydrogen, I go 3 sig figs to give me basically at least 4 total sig figs on that atomic weight that I'm using. For carbon, I probably most ordinarily just stop at 12.01. It's just like that's by habit what I tend to use in most problems, as opposed to going 12.011. Now, if you're doing a lab problem and you have like measured on a balance a mass out to like 5 or 6 sig figs, you're probably going to want to look up a more precise formula weight, which you could do by going to, a C or C index, looking up atomic weights there. You can just go to Wikipedia, usually is an easy source for looking up a more accurate formula weight. So use the number of sig figs for like the mass you have as the driver for how many sig figs you need on your atomic weight. So be more precise when you're using more precise masses. That usually happens in the lab. For textbook examples, you're usually converting like a mass to 3 or 4 sig figs. So using like 3 or 4 sig figs with your masses is going to be more than enough. So also, I should be doing 2 times the hydrogen. I don't know why we're at 1. So we have 2 hydrogens in the formula, so 2 times the hydrogen mass. So we go 2 times 12.01. Plus 2 times 1.008. It gives me a mass of 26.04 atomic mass units. In a slide or two, we're going to get into like grams per moles. If you've already seen this or if you know this already, and we can even start thinking this way, this will also be 26.04 grams per mole. But we'll see in a minute why that is and what the mole is if you're not sure. So if you've seen this before, maybe that makes sense. Maybe if we start thinking now, we can use the periodic table to get the AMU, the mass of the molecule in atomic mass units, or the mass in grams for a mole of the substance. That these two would be kind of synonymous numbers with each other. Now, for K2SO4, the only weird thing for K2SO4 is it's not really a molecular compound. So usually for like K2SO4, usually we're just going to talk about its formula weight. And it's not a molecular compound, so usually we don't talk about its molecular weight. It's not a molecular compound, it's an ionic compound. So for ionic compounds, we usually only talk about their formula weights, the weight of the formula. It's the exact same number, it's the exact same process. It's the exact same idea of taking 2 potassiums plus a sulfur plus 4 oxygens, mass, and adding them up. Same process, but we're just trying to make sure we think of K2SO4 as not really being a molecule. Like when you have K2SO4 in a solid form, you have sulfate, potassium, potassium, in a linear sequence with a bunch of ions repeating through the structures. You have like sulfates with like 2 potassiums here, another sulfate, 2 potassiums, another sulfate, in all 3 dimensions. So K2SO4, not a molecule, doesn't have a molecular weight. It has a formula weight. It's the exact same number you would establish as its molecular weight if you were thinking about the molecular weight. So the formula weights and molecular weights synonymous with each other for molecular compounds, and then we just don't really have a molecular weight for an ionic compound. Very small, nuanced detail, but the process is the same of determining the formula weight. So potassium, 39.10. Sulfur's 32.06. And then oxygen 16.00. I get 174.26 as the formula weight for potassium sulfate. Now again, nuanced detail, molecules have molecular weights and formula weights. Ionic compounds have formula weights. Same process for determining them, of just adding up the masses for all the atoms in the formula. Now let's get into the topic of composition. A couple slides from now we'll get into kind of going in reverse here, of giving you percent composition data and then asking you to find a formula. So you might remember these problems. Sometimes they're hard to forget solving this. You may forget how to solve the problem. You probably remember those problems where we say something is like 15.5% H, 60 point whatever percent C, whatever percent O, what's the formula of the compound. You might remember these from high school. We'll go over those in a minute, but for now we're gonna kind of go the other direction. We're gonna say, if you know the formula, can you tell me the percent composition? That's actually very easy. The percent composition from a formula of a given atom is just a percent by mass. So the percent, say, carbon by mass in a formula would be the number of C atoms times the mass of C. Let me even be more precise here, the atomic mass, or the atomic weight of carbon, divided by the formula weight of that compound or that unit. And then this is going to be times 100%. So if we were saying what's the percent C in CH2O, we would say, okay, we have 1 carbon times 12.01 AMU as the atomic weight of carbon. And then we're going to divide by the formula weight. So the formula weight here would be 12.01 plus 1.008 times 2 plus 16.00. So the formula weight is 30.03. So the percent by mass of carbon in CH2O would be 12.01 divided by 30.03. So that's 39.99%. So 39.99% of the mass of that compound would be due to the carbon atoms in the sample. The percent by mass of hydrogen would be the 2 hydrogens times 1.008 AMU divided by 30.03 times 100%. So hydrogen's light, so this isn't much of the sample. So I get 6.71%, 6.713% hydrogen by mass. Now the percent O, you could probably determine it by difference, right? 100% of the sample is CH or O, so the remainder of the mass should be oxygen. So we could subtract 100. We take 100 minus this, or we can just go 16.00 times 1 for the 1 oxygen, divide by 30.03 times 100%. We are percent O. So 53.28%. And if, just to do the simple, obvious task of making sure these add up to 100, 99.98. So within some small rounding, we're getting 100% here. And so on one hand, we're just seeing how you calculate percent by mass. But let's think of this compound here, which might be the formula of glucose. But notice, and we talked about empirical formulas before, that the empirical formula of C6H12O6, like the simplest ratio of C to H to O, in that compound, if we divide all those by 6, we get C1H2O. So the empirical formula would be CH2O. Now, that doesn't, like we talked before about how that doesn't mean much. You know, like when you say formaldehyde is CH2O, that's a molecule that has that formula. And then glucose is C6H12O2, and they share the same empirical formula. They share no properties because of that. There's nothing special between those two molecules because they share the empirical formula. But they do share one detail. That is, they're, of course, going to have the same percent composition. So they will have the same percent composition if they share the same empirical formula. So we'll just do this for one of the elements in C6H12O6. For this other molecule here, if we wanted to calculate the percent carbon and just make sure we get 39.99% or about 40%, we're going to take 6 times 12.01 AMU. For the 6 carbons in that formula, we just have to come up with the formula weight of 6 times 12.01. And some of you are probably sitting there thinking, why don't we just do 6 times 30.03? If you're thinking that, that's very intelligent. That is correct. That would give us the right mass. Because if you were thinking we just have 6 units of the CH2O, you might have just been saying, well, isn't the atomic weight of glucose just 6 times that? And that is exactly the mass. But it's 180.16. When I add it all up from 12.01, 1.008, 16 times the appropriate number. So 6 times 12.01 divide by 180.16 times 100% is 39.99. It actually is rounding to 40.00%, but the same percent composition. So we're getting the same percent carbon. I'm sure you agree with me that we would get the same percent by mass hydrogen, the same percent by mass oxygen. Okay, so with this problem, what I hope the slide is showing us is if I give you percent composition data and say, can you determine a formula from that? Yes, you can determine a formula. It's going to be the empirical formula. So if I told you some compound had a composition of 40% by mass carbon, 6.71% hydrogen, and then 53.28% oxygen, you wouldn't be able to tell me the molecular formula from that information. You would be able to tell me the empirical formula, the simplest ratio of those elements to each other, but no other information than that. And so that's an important topic when we get to percent composition data, that we can get back to the empirical formula, and then maybe if we give you a molecular weight from some other experiment, you can then determine the molecular formula. So we'll do those problems probably on Monday. I don't know if we're going to get to those today or not. But let's take a sidetrack and talk a little bit more about Avogadro's number. We've already introduced it because it's our conversion factor between AMU and grams. If you remember, we established in the last chapter that 1 gram is equal to Avogadro's number of AMU. So we might remember seeing Avogadro's number in chapter 2 when we were converting grams to AMU, or if we thought about the conversion factor between AMU units and gram units. So the AMU unit is really, really small. If you invert Avogadro's number, it's like times 10 to the minus 23 or times 10 to the minus 24 grams. So 1 AMU is a really, really small amount of mass. Now, here in chapter 3 is where we formally define the mole. So 1 mole of anything, so say 1 mole of X, is equal to 6.02214,179 times 10 to the 23 like units of X. Like this units word here is a little tricky to know what this is. Let's give an example in a minute of what we mean by units of X. So let's imagine we have a mole, and we talked about this a little bit in the last chapter. If you have a mole of carbon, let's even picture a mole of carbon-12, because we were talking about this in the last chapter. This would equal 6.022 times 10 to the 23. Carbon-12 is an atom. So we'd have the unit there is the atom, so we'd have that number of atoms of carbon-12. So a mole of the carbon-12 atom gives us an Avogadro's number of that atom. We could have 1 mole of H2. So we have a mole of molecules of hydrogen. So 1 mole of the molecule of hydrogen would be 6.022 ... times 10 to the 23 molecules of hydrogen. So you just have to think, what is the item that we're talking about? What's its unit? Well, H2, the unit would be the molecule. So a mole of the molecule of hydrogen is an Avogadro's number of hydrogen molecules. And then let's do one more example. So if you had 1, or maybe 2 more examples. 1 mole of I don't know why sometimes I write, when I'm trying to write C6, I start writing 6. C6H12O6. So a mole of glucose would contain an Avogadro's number of molecules of that formula. Now, one that gets a little confusing to me is when I start thinking of an ionic compound. So if I said you had 1 mole of that example we were talking earlier, of like K2SO4, where it's not really a molecule. The word molecule is so useful. It's so easy to think of molecules, I think, because and I don't know if you think of it as easy as I do, it's like thinking of 2 actual H atoms bonded together as H2. Thinking of some collection of 6 carbons, 12 hydrogens, 6 oxygen atoms, somehow that being 1 molecule, that's a molecule of glucose. Now when I start thinking of K2SO4, I'm like, well, how are they situated? How does this thing really look? It's harder for me to picture these ions. I'm not quite sure where they're going to be situated in 3 dimensions relative to the sulfate, but somehow they are. So 1 mole of K2SO4 would be 6.022 ... times 10 to the 23. This is here where almost that word units works better. So maybe like formula units. Where the formula unit is kind of like the molecule that we think of for, it's like the simplest ratio of the ions in K2SO4 is that formula unit. So I have that many units of K2SO4. So kind of circling back to this, units at the start of this was like kind of confusing on what we would mean by units of X. Units often a molecule if we're dealing with molecular compounds, or it could be atoms if we're dealing with an atomic sample, or it could be like the formula unit if we're dealing with an ionic compound. An Avogadro's number is a tremendous number. There's an example in the book of if you had an Avogadro's number of like nickels, of the coin of a nickel, like how many times could you wrap the equator in nickels if you had an Avogadro's number? And the answer is like 300 trillion times or something like that. Like just to think about just having like what we think of as an Avogadro's number, where for a water sample, like a sample of water, to have an Avogadro's number of water molecules is about 18 grams. That's about 18 mils of water. So you have about 18 milliliters of water, but then expressed in Avogadro's number, you have an 6.022 times 10 to the 23. If instead of that being the small molecule, it's a nickel, 300 trillion times around the equator of the Earth, just to show how small atoms are, and just how small at the atomic scale or the molecular level these substances are. Well, let's get into molar masses versus molecular weights, conversions into the mole, and in that gram per mole scale. And so a molar mass is usually, from the word molar, is usually in that gram per mole scale. Molecular weights are often in AMU, and then usually we don't state this with the mass, but we should. It would be a little bit more clear. It's like the AMU per molecule, or the AMU per unit. So it's the mass of the unit of that substance. And often we just write this as AMU. and the per like molecule or per unit is understood. And so let's just give an example of how we can sort of convert maybe the atomic weight of something like water into grams per mole, just to see how easy it is. Because we've already kind of mentioned that if you take something like water, so do the 2.016 off the periodic table. So if that's AMU, we go 1.008 times 2 AMU, and then add 16 to that, we get 18.02 AMU. Now that's per molecule. If I want to get the number of grams per mole in water, starting from 18.02 AMU, now we understand it's per molecule, per individual water molecule. Then we can use Avogadro's number. If we want to convert to per mole, we just have an Avogadro's number of molecules per mole. So 1 mole of water is an Avogadro's number of water molecules. And then our AMU mass converts into grams with that same Avogadro's number. So we have an Avogadro's number of AMU in 1 gram. So we do 18.02 AMU per molecule, convert to moles, multiply by Avogadro's number, convert to grams, divide by Avogadro's number. So we're multiplying by Avogadro's number and dividing by Avogadro's number. So this is how we come up with 18.02 AMU is the atomic mass, unit mass of 1 molecule of water, and it's also the molar mass, 18.02 grams per mole. So a mole of water, 18.02 grams, a molecule of water, 18.02 AMU. And again, if you're confused, why does it work out this way? It's just because of the way we define the AMU scale if you go back to chapter 2. So it's just all based on us defining the AMU conversion factor to be the same conversion factor into grams as it is for the molecule count into mole. So it's a very intentional result that we get the same number here. Okay, now, so the mass of 1 molecule of water in AMU is 18.02 AMU. Well, what's the mass in grams? What's the mass of 1 water molecule but expressed in grams? So if we had 1 water molecule, but we want the mass in grams, this is where we use the conversion factor starting with 18.02 AMU is the mass of 1 molecule in AMU. This conversion here is just the Avogadro's number per 1 gram. So to see the mass of 1 single water molecule, just to work it out in terms of grams, we do 18.02, divide by Avogadro's number. .99 times 10 to the minus 23 grams. Really, really light, obviously. Just to kind of like think of how do you get the per gram for 1 single molecule, we just take the AMU mass, convert to grams. You could take the gram per mole mass and then also 1 mole, Avogadro's number, so you can take the 18.02 grams per mole number and just go moles to molecules and also divide by Avogadro's number, come up with the exact same number. So really small mass per molecule for water. Now, one of the main things we do in chapter 3 is go from like grams to moles. So using the molar mass to convert the mass of water, let's say you have 25 grams of water. You can use the molar mass to convert to moles. We can then convert to particles using Avogadro's number. We can convert to atoms using the formula. So we'll do a few examples. We'll start from this slide next time on how we can take a certain mass of water and convert the moles present, the atoms present, molecules present, all those fun things. All right, guys, that's a good stopping point for today. Have a great rest of your Friday and a great weekend.